next topic is going to be statics. So on its face, the statements for statics are actually very simple. They're actually a reduced form of the equations that we had for torque. But as many of you know, working some of these problems, that's not quite as easy as it sounds. So I'm going to lay out the equations first and talk about them. And then I'm going to list a couple of things that I think are tricky points about statics, and I'm going to try to address those, and then at the end I'll work a problem. So to start with, the condition that something's in static equilibrium is that the sum of the forces, the sum of the vector forces, is equal to 0, and the sum of the torques, also a vector, is equal to 0. Okay, so like I said, this is like what we had for torques, only a little bit simpler, because when we had torques before, we said that each one of these equations was not equal to 0. In the case of the sum of the forces, this was equal to the mass times acceleration, and in the case of the torques, this was equal to the moment of inertia I times alpha. Okay. So you can see what we're really trying to say here when we're looking at the case of static equilibrium. We know that that means that something's not moving, but we can really see that in these equations now that I've written in this way. Because if we say that the sum of the forces is equal to 0, the linear acceleration is equal to 0. And if I say the sum of the torques is equal to 0, then the angular acceleration is equal to 0. So let's talk about some of the things that are tricky about statics. The first thing has to do with the fact that I say that the sum of torques is equal to 0, but we know from our previous discussion, saying that the sum of the torques doesn't mean anything in and of itself. We need to say that the sum of the torques is about a particular point. And so when it comes to statics, the sum of the torques being equal to 0 means that the sum of the torques about all points is equal to 0. So let's say that here, sum of the torques about all points is equal to 0. So let's investigate what this statement means. Let's say I have this bar, and it's supported on one end with a pivot point, and the other end right here. When I say that the sum of the torques about all points is equal to 0, that means that I can choose a lot of points of rotation. So I could choose this end to be a point of rotation. I can choose this point to be a point of rotation. I choose the middle of the bar to be the point of rotation. I can choose this point to be the point of rotation. You can see and on ad nauseum, right? Because there's an infinite number of possibilities for the point that I choose here. So when I say the sum of the torque about all points is equal to 0, I mean you have to choose a point first. So you have to choose a point to sum the torques about. And we know from our previous discussion that the torque is going to be equal to R times F perpendicular. And this is where this R, again, becomes very important. It's worth going back to the last video and reviewing this if this is still a little bit confusing, because I talked about this in even more detail. But what this R means is it's the distance from the point of rotation to F perpendicular. And so when I say that the sum of the torques about all points is equal to 0, it means I have to choose a point, and this R has to be relative to that choice that I make. Okay? The next part that's tricky about torques is finding what F perpendicular is. So finding F perpendicular. And really what that comes down to is this a sine or a cosine of an angle? There's not an easy answer to that, because it depends on what the angle is given. And you need to apply some trigonometry in order to figure out whether I want to use the sine or the cosine. We'll see in some more detail when I do the example problem how that ends up working out. The third thing that's tricky about torque has to do with the fact that torque's a vector. So I've been writing that this torque is a vector, which means that clockwise and counterclockwise are opposite directions to each other. And so I need to choose a direction that I'm going to say is positive. So torque is a vector is an applied torque in the clockwise or counterclockwise direction. So once we determine whether it's clockwise or counterclockwise, we usually say counterclockwise is positive and clockwise is negative. Again, when I work the example, I think this will be more clear. So the next thing I'd like to do is to talk more about this point. How do I know whether f perpendicular is going to be a sine or a cosine, or maybe there's not a trigonometric identity there at all? Okay, let's see how that works. So we want to investigate that point 2 that I had on the previous slide, and that's when I want to find f perpendicular, is that going to be a sine, is it going to be a cosine, or is it not going to be either one of them? So here what I did was I set up 3 different scenarios, and what we're going to do is we're going to see what the torque is about the red points that I have here. If you need help visualizing what's happening here, because this is kind of abstract because I just have these arrows drawn here, you can think about what's happening in terms of this diagram in the bottom right of this wrench. So for the wrench, we have this distance r, that's going to be the distance from the point of rotation that I have at the center, and the forces that I'm applying here. So let's look at case 1. So case 1, we can label this, so we have, this is going to be r, the distance from the point of rotation to the force, and then we have this force that I'm calling F1. And so the question is, what is torque 1? Okay. In general, this is going to be equal to r, the distance, that here happens to be exactly the same thing, times f perpendicular. Okay. So the question is, what is f perpendicular to r? In this case, we have F1 is actually already perpendicular to r. So here, torque 1 is just going to be equal to r times F1. Okay, now let's look at case 2. Now for case 2, we have this F2 that's going to be going at this angle here that I'm going to call theta. Okay, again, we have the same distance r here. And now what we want to ask ourselves is, what is torque 2? Again, in general, the torque is going to be equal to r times f perpendicular. Okay, r is still the same r that we had here, so this is r. And now what we want to ask ourselves is, what is the component of F2 that is perpendicular to r? So we have this triangle we can complete here. Okay, so we have 2 sides. We have this side, and we have this side. Okay, now we know that F2 is going to be the hypotenuse of the triangle, and so the perpendicular part that we want is going to be this side. Okay, so that side is going to be F2 times cosine of theta, because the cosine is going to be the adjacent over the hypotenuse, and this is the adjacent side to the angle. Okay, so this tells us then that r times f perpendicular for the case 2 is going to be r times f2 times cosine of theta. Okay, now let's look at case 3. Again, we have the same distance r here. We have this f3. But now, the angle that I have here is going to be this angle. Okay? So, starting as we always do, we say that the torque 3, is going to be equal to r times f perpendicular. So what is f perpendicular in this case? Well, we can, again, complete this triangle here. And the part that's perpendicular to r is going to be this part, which is going to be f times sine of theta. So that tells us that torque 3 is going to be equal to r times f times sine of theta. Okay, so you can see in these 3 different scenarios, there are three different ways that we're writing this in the end when we're writing it in terms of the angles that are given. So in the first case, the angle is 90 degrees. So F perpendicular is just that force. In the second case, the angle that I'm given is between F2 and this vertical here. So that means that the perpendicular portion is F2 times cosine of theta. And in the third case, the angle that's given is between F3 and the direction that R is going in. So this is going to be R times F3 times sine of theta. Okay? So the next part we're going to talk about is going to be the problem-solving strategy that we can apply here. And I'm going to do an example of a problem that we can do with torque. Okay, so let's talk about our problem-solving strategy for statics. The first thing that we want to do is to draw a free body diagram for the object that is rotating. Okay. Second, we want to determine the number of unknowns, and this is going to tell us how many equations we need. Okay? Right? Because if we have two unknowns, we need two equations, three unknowns, three equations, so on and so forth. The third thing that we want to do is to write down Newton's second law for translation and rotation. The fourth thing is going to be to refer to the free body diagram to write the sum of forces equations. Number 5, we need to pick a point of rotation to sum the torques. Now, a good choice, and this is an important point, a good choice minimizes the number of torques in the equation. Okay, so we had this problem that was pretty challenging on one of the tutorials, and so I'd actually like to just go over that problem. What you had was you had this diagram that I have on the right. You have a bar with mass capital M and a mass lowercase m. This mass is going to be hanging from a string that's attached to the end. This has some total length, so total length L, and this wire, the horizontal wire, is connected at a point 3/4 L. Okay. There's also some angle of theta right here. And so what we want to find is we want to find what the tension is in this string. We also want to find the forces at the pivot point at the wall. Okay, so right here. So there should be some force that is going to be up. We'll call this some N1. And there should be some force N2. All right, so let's go through our problem-solving strategy. So first thing that we want to do is we want to draw a free body diagram for the object that's rotating. So that's just going to be the bar. So we have the bar. And now we want to draw all of the forces that act on this bar. So the first force that we can draw is just going to be its weight force at its center of mass. So there's going to be some weight that's going to be capital M G. Okay. We also have this weight that's hanging off of here, and so that's going to exert a force of lowercase mg. Then we have the tension. So tension. And then these two forces here, the N1 and the N2. Okay? So we've drawn our free body diagram. That's step 1. Okay? Step 2. Now we want to determine the number of knowns and unknowns. So what do we know here and what don't we know here? We know what these masses are, so that's good. We know what the masses are. But we don't know, I'll underline what we don't know in blue. We don't know the tension, and we don't know these two normal forces. So we have 3 unknowns. Okay, step 2 completes. All right, now let's look at step 3. Step 3, we want to write down our Newton's second law for translation and rotation. So for translation, this is the sum of the forces is equal to the mass times acceleration, and the sum of the torques is equal to I times alpha. So these are the general forms, but remember we're in statics. So that means that these equations are both equal to 0. All right? So now let's expand our sum of forces equation. So we can say that there's some force of x, some force x is equal to 0, and some sum of forces in y. Let's do this over here. It's also equal to 0. Okay. Step 3, done. So we know the equations that we need to use. Step 4, we want to refer to the free body diagram to write down what the sum of the forces are. So first thing that I need to do, and actually I probably should have listed this in my problem solving strategy, we need a coordinate system. So let's draw a coordinate system, and that's going to say that this is going to be the positive x direction, and this is going to be the positive y direction. Okay. So let's look at their sum of forces in y. What forces are we going to have in the y direction? So we can look at our diagram, and we can see that N1 is going to be in y, and it's also going to be in the positive y direction, so this means that this is going to be N1. What else do we have in y? We have capital Mg, which is down, so this is going to be minus capital Mg. And then we also have lowercase mg, which is also down. So this is minus lowercase mg. And the sum of the forces should be equal to 0 because we're doing statics. Okay, good. So now let's look at the sum of forces in x. So when we do our sum of forces in x, it's actually a little bit easier here because we only have 2 forces. So we say that N2 is going to be in the positive x direction, so this is going to be N2. T is going to be in the negative x direction, so this is minus t is equal to 0. Okay, so far so good. This isn't too bad. Now what we want to do is to actually do the harder part, and this puts together all of the things that we've been talking about so far. So step 4 is done. And now let's look at step 5. We need to pick a point of rotation to sum the torques. And the best choice that we can make is going to be the one that minimizes the number of torques. So let's consider a couple of different cases that I could pick. We could pick this point at the bottom. We could pick the point in the middle. And we can pick this point here. Okay. So if I pick the point all the way at the top, that does minimize the number of torques in a way because the torque in general, remember, the torque in general is going to be equal to r times f perpendicular. And if I choose the point all the way at the top, then the small mass is going to exert a force at that point. So the distance to it is 0. So that gets rid of one of them if I choose that point. The same thing is true if I pick the middle of the bar because the torque from the beam about the center of the bar is also 0. But there actually is a better choice, and that's to choose the point at the bottom. Okay? So we're going to choose the point at the bottom because it gets rid of 2 torques. N1 and N2 both act at that point. Okay? So we've identified the point that we want to sum the torques about. So now let's sum the torques about that point. Okay? So this is the point. So we can write down our sum of torques equation. And we have this angle here. This is the angle theta. Now this is where things are going to get a little bit tricky in terms of how are we going to set up what the angles are. Okay? So when I'm looking at the sum of torques on this one, I can walk across the beam starting at the point and then ask myself what are the forces acting as I go out there and what is that distance. So I walk along the beam and I get to this point, which is going to be N1 L divided by 2, right? So that's where the first force acts. So we have L divided by 2, that's R. Remember that we're using this equation here. We're using that equation for every one of the torques that we're summing here. So we have this L over 2 times the force that's perpendicular to that. So let's look at this M. This M we can break into components. We have some component here and we have some component here. And the question is, based on the angle that I give you here, what is this component, right? Because that's the component we want. That's the perpendicular part. And so we can see, if I draw another line here, let me extend this line here and this line here, that I have a setup here where I have two parallel lines that are crossed by another line. And so what that tells me is that this angle here, that angle there, is theta. So if I know that that angle is theta, then the component that is perpendicular to r is going to be mg times sine of theta. So we have mg sine of theta. Okay. Now the next question is this going to rotate in the positive or the negative direction? Is it going to go clockwise or it's going to go counterclockwise? And so if we look at this mg is going to make this go down, which is going to be rotating in the clockwise direction. And the convention that we use is clockwise is negative, so this is negative. Okay. Now let's continue along this bar, and so we're now going to get out to this point where t is. This is going to be at a distance 3/4 L. And now what we need to do is we need to find what t perpendicular is. So what we can do to figure that out is to say that we can complete this triangle here. Let me use a different color. This forms a full triangle here, right? And we know that the angle is theta right here. So the question is, what is the angle here? So we can figure out what this angle is here by saying that it's 90 minus theta, right? Which means that this angle is 90 minus theta. And so the part that we want is the perpendicular portion here. Okay. Which means that we want L times t. And this perpendicular portion, if this is 90 minus theta, this is going to be sine of 90 minus theta. Or we could also say that this is cosine of theta. Okay. Because sine of 90 minus theta is equal to cosine of theta. Okay? Now, is this going to be positive or negative? This is going to cause us to rotate in the counterclockwise direction. And we're saying that counterclockwise is positive, and so this one is positive. Okay? Last piece. Now we're walking all the way out to the end. This is a distance L. And we want to find what the force mg is perpendicular to that. So that's going to be this component. Okay, and that triangle is similar to the one that we had for capital MG. So this is going to be L times mg times sine of theta. Now, is this one positive or negative? This one is negative. Okay, and this whole thing, the sum of the torques is equal to 0, and so this is going to be equal to 0. And so we have our three equations. Equation 1, equation 2, and equation 3. That's actually on a couple of different lines. Okay? The next video is going to be over angular momentum, and what we're going to see again is there's going to be parallel between angular momentum and linear momentum, but there's also an interesting parallel between torque and angular momentum. So we'll explore that in the next video. I'll see you guys there.